Hello students, a very warm welcome to all of you at AriserTalent. How are you all? I hope all of you are doing just amazing. So students, today we are going to deal about few of the NCERT questions that is related to our chapter Human Eye and the Colorful World. So we have ended our session with our last topic, that is about the atmospheric refraction, and we have seen various things that are occurring in the nature due to such sort of refraction. So today we are going to deal about the NCERT questions here. So we have a first question of the sequence, and the question of this sequence is: the human eye can focus the objects at different distance by adjusting the focal length of the eye lens, and this is due to. Okay, so human eye has a tendency, it means whenever a light is going to fall on a human eye, what will happen? It has a tendency to adjust the focal length. It can increase or decrease the focal length accordingly, and we know that process, or you can say that this capability of the human eye is actually known as the power of accommodation of the human eye. Okay, so the options here are presbyopia, accommodation, nearsightedness, or farsightedness. So we have the correct option, that is accommodation here. Okay, so option B is correct in this case. So this is the accommodation of the human eye. Now let's move forward to the next question we have. The human eye forms the image of an object. Okay, so you have to identify that where the image is going to be formed in case of a human eye. We know that there is a screen where the human eye is going to form the image, and this image is actually known as the retina of the human eye. So which is the correct option here? Cornea, iris, pupil, or retina? So you have the correct option, that is option number D. So image is going to form on the retina here. Clear? Now let's move forward to the next question. The least distance of vision for a young adult with a normal vision is about. So whenever a person is young, the normal vision for that person is 25 centimeter, and the far point for that particular eye will be infinity only. So what is the least distance of vision for that person? The normal vision for that person will be 25 centimeter. So you can see that option number C is correct in this case. So you have a correct option, that is option number C. Okay, now let's move forward to the fourth question of the sequence here. The change in the focal length of an eye is caused by the action of. It means the eye is able to change the focal length. It can increase or decrease the focal length accordingly, and this power is known as the power of accommodation of eye, and this is basically caused because the ciliary muscles have a ability to contract or expand. So the options here are pupil, retina, ciliary muscles, or iris. So the correct option here is ciliary muscles you have. So we have option number C correct here. Clear? Now let's move forward to the next question of the sequence. And this is the numerical problem you are provided here, and the question is saying a person needs a lens of power minus 5.5 diopters. So firstly, I am writing the given conditions here. Now what is given in the question? A person is needed a power of minus 5.5 diopter. Okay, so the power it is needed is 5.5 diopters in negative. For correcting his distance vision, for correcting his near vision, he needs a power of plus 1.5 diopter. So the first thing you are given the power, this power is for the distant vision. This is a power for distance vision. Now in the second case, the power you are provided is plus 1.5 diopter. So if the power is plus 1.5 diopter, this power is basically for the which purpose? It is for the near vision. Okay, now what is the focal length of the lens required for correcting the distant vision and the near vision? So we have to solve the two parts here, that is how much focal length will be needed for the distant vision, and secondly, how much focal length will be needed for the near vision. So we are solving the first part here. In the first part, we know that the power is given by a formula, that is 1 upon focal length. Okay, this is the formula for calculating the power. Power will be equal to 1 upon focal length. It means P equal to 1 by F. So if I am solving the first part, that we are calculating the focal length for the distant vision, it came out to be F will be equal to 1 upon P, and it is going to give you the value 1 upon minus 5.5. So if I am shifting the 0 here, it is 5 to are 10, it will be 11, and it is 2 upon 11. So how much 2 upon 11 will give you? The 2 upon 11 will give you a value, that is 11 1 are 11, there comes a 9 and 0.18, and it will be in the negative. So 0.18 will be the focal length for the distant vision you have. So the correct answer we have is minus 0.18 centimeter. It is minus 0.18 centimeter, that is the focal length for the distant vision. Now I am solving the second part here. You can see in the second part, again we will use the same formula, that is equal to F equal to 1 upon P. Now the power given is 1.5 here. Okay, so it is 1 upon 1.5. So if I am going to solve this problem, I will get 5 2 are 10, 5 3 are 15. And what is the value of 2 upon 3? It is going to give you 0.6, 0.6 and 0.667. Okay, and again it will be in meter. So the focal length came out to be 0.667 meter in this case. And this is the same unit we have. This power is also in the unit of meter, because the standard power for the focal length will be meter, and power is again given in the standard units, that is diopters. So in both the cases you are getting the focal length. The first part is for the distant vision, and the second part you are getting here is for the near vision. Okay, so this is the very simple numerical problem from our NCERT. Now we are moving forward to the next problem we have. The far point of a myopic person is 80 centimeter in the front of the eye. What is the nature and power of lens required to correct this problem? Okay, the question is basically based upon the defects in the human eye. Now, whenever we are solving any question here, firstly we will write the given conditions that is provided in the question. So the given conditions in the question is, the far point of a myopic person is 80 centimeter. So the far point is given here. Far point equal to 80 centimeter. Okay. Now what is the nature and power of the lens required to correct this problem? So you have to find out the nature and the power of lens required in this question. So firstly, whenever there is a myopic eye, it means the image is going to formed just below the retina. So if the image is forming below the retina, then the person is not able to see the image very clearly. So this defect is basically corrected by using a concave lens of suitable focal length here. So what we are using? We will use the concave lens. This defect is corrected by concave lens. And what we have to identify? We have to identify the defect is basically corrected by using the concave lens. So what we have to find out in this case, you have to find out the power of the lens here. So if I want to determine the power of the lens, what should I know first? I should know the focal length of that particular lens, because you know that whenever you are going to determine the power, the formula will be 1 upon F. Okay, So you must needed a focal length in this case. So how could the focal length be find out in this case? The focal length will be derived by using the lens formula here. So what you are going to apply? You are going to apply here the lens formula first. Okay. Now what is lens formula? The lens formula is 1 upon f will be equal to 1 upon v minus 1 upon u. So this is the lens formula we have. Now for the myopic eye, the far point is 80 centimeters. So what you are given in this case? You are given that v equal to 80 centimeter. Okay. And what is the u in this case? The u in this case will be infinity here. U will be infinity here. And for this v, we have to take the negative sign in this case. Okay. Now when I am going to substitute these value in this lens formula, what I will get here? I will get 1 upon f equal to 1 upon v. It means it is 1 upon minus 80 minus 1 upon infinity. Now 1 upon f will be equal to minus 1 upon 80 and 1 upon infinity will give you the value equal to 0. Okay. Now f will be equal to minus 80 centimeter. So you can see that the focal length is minus 80 centimeter in this case. Now what you want to find out? You want to find out the power of the lens. So power will be equal to 1 upon f and it will be again minus 1 upon 80, and how much it will come out to be? Whenever you are going to divide the 80 by 1, here it is 80, it is 1, it will be 0.0, 80 here, here it will be 20, 1 0 shifted here, 8 to 16, so it will be 160 here, then it comes 40. If I am again substituting one value, it will be 0.0125. So the power of this lens will be minus 0.0125 and the power will be in diopters. Okay. So the power of the lens came out to be minus 0.0125 in this case, and you can see that the power is negative, and if the power is negative, the lens that is needed for correcting the myopic eye will be the concave lens only. Okay. So the power is negative. So what you are using here? You will use the concave lens in this case. So this is a final solution of this problem you have. So I am once again repeating this question. You are provided with the myopic eye, and for the myopic eye, the near point is at the infinity and the far point is taken as a v equal to minus 80 centimeter. Now for calculating the power, we are required the focal length first, and for calculating the focal length, what you are needed? You are basically needed the lens formula for sorting out this problem. Okay. So you will needed the power of minus 0.0125 diopter and the power is negative. So this defect is corrected by using the concave lens of suitable focal length. Okay. You can copy this solution from here, so we can proceed to our next problem. Now let's see the next problem here. Make a diagram to show the hypermetropia is corrected. The near point of the hypermetropic eye is 1 meter. What is the power of lens required to correct the defect of vision? Assuming that the near point for the normal eye is 25 centimeter. Okay. Now you have to correct the hypermetropic eye. So in case of hypermetropia, the image is going to form beyond the retina. If the image is going to form beyond the retina, you will correct this defect only by using the convex lens of suitable focal length. So how will be the hypermetropic eye will show to you. So if I am assuming that this is the eye we have, So this is the condition for the hypermetropic eye. You can see that this is the retina you have, and the image is not forming on the retina. The image is going to form beyond the retina. If the image is going to form beyond the retina, how you will analyze the image on the screen? So you have to correct this defect only by using the convex lens of the suitable focal length. So what you will do? You will use the convex lens here. So if we use the convex lens here, we will get the image exactly on the retina, and this image is going to be visible to you. Okay, so we will use the convex lens in this case. Now we have to find out the power of the lens required to correct this defect. Now you are given that the near point of the hypermetropic eye is 1 meter. Okay, the near point is 1 meter. So you are given that V equal to 1 meter, and 1 meter will be equal to 100 centimeter, and you are given that the near point for the normal eye is 25 centimeter. So you will assume U will be equal to 25 centimeter. Okay, now this will be in the negative and this will again be in the negative sign. Now if I want to find out the power of the lens, again I will require the focal length for that lens. So focal length can be found out from the lens formula. We will use the lens formula in this case. The lens formula is 1 upon f equal to 1 upon v minus 1 upon u. 1 upon f will be equal to 1 upon minus 25 minus 1 upon 100, and this came out to be minus 1 upon 25 plus 1 upon 100. Okay, so 1 upon f will be equal to 100 here. Here it came out to be 4. And here it will be the plus 1. Okay, now f will be equal to 100 upon 3. No, it will be equal to 100 plus 5. The v will be positive in this case and u will be negative in this case. So f will be equal to 100 upon 3, and 100 upon 3 will be equal to, it will be equal to approximately 3.33. So it will be 100 upon 3, and 100 upon 3 is going to give you the value 3.33 in this case. Okay, now we are getting the focal length that is equal to 3.33 centimeter. Now what you have to identify in this case? In this case we have to identify the power here. Okay, we have to calculate the power of the lens. Now the power of the lens P will be calculated as 1 upon f, and f came out to be 100 upon 3, so it will be 3 upon 100, and this power will be equal to 0.03 diopter. So if I am going to convert this centimeter into meter, so for converting centimeter into meter, I have to divide this focal length with 100. Okay, so you will get the focal length in meter here. So this is equal to f equal to 100 upon 3. This is in centimeter, and if I am dividing it by 100, 100 will be cancelled by 100, and this f came out to be 1 upon 3 meter. So if focal length is 1 upon 3 meter, so the power will be the 3 upon 1, and 3 upon 1 will give you the value 3, that is equal to 3 diopter. So it will be 3 upon 1, and the power came out to be 3 diopter in this case. Okay, and the power is positive here. So if the power is positive, the defect is corrected by using the convex lens only. So the final answer for this problem is that you can correct this defect by using the convex lens, and secondly, the convex lens will have a power of 3 diopters. Okay, so this is the final answer you have. So this is again a very simple problem that is based upon the defects of correction and power of lens. So you can see that how important this topic is from your CBSE point of view. Now let's move forward to the next question here, and the next question is, why is normal eye not able to see clearly the object placed closer than 25 centimeter? You know that the normal distinct of vision for a normal eye is 25 centimeter. It means up to 25 centimeter you can see very clearly. But if the distance is not 25 centimeter, what will happen in this case? If the distance is not 25 centimeter, the ciliary muscles will not bulge the eye lens, and in this case the image is not going to form on the retina, and the things you will see and it will appear very blurry to you. Let us take a simple example. Whenever you hold any book very clear to your eyes, you can see that the words and the letters that are written in the book appear very blurred. That's why they are appearing, because the ciliary muscles will not able to blur, ciliary muscles will not able to bulge the eye lens to the such extent. So what will be the answer for this problem? The answer for this particular problem is that the ciliary muscles will not contract. The ciliary muscles contract and bulges the eye lens, and in this case image is not formed on retina. And the image is not going to formed on the retina, the image will appear blurred in this case. So you will see that the image is going to be blurred in this case if you will hold the book or you will see a distance of vision less than 25 centimeter. So this is a theoretical question you have. Now we are moving forward to the next question here, and the next question is, what happens to the image distance in the eye when we increase the distance of object from the eye? So the question is saying, if you are changing the distance of the object from the eye, what will be the effect on the distance of the image? Suppose if I am holding this object at the different positions, okay, if you holding this object at the different position in front of your eye, the image is going to form at the different points on the retina. So image distance will not have any effect if you are changing the distance of the object, because the image is going to form only at the different positions on the retina here. Okay, so let's write the answer of this problem. Image distance in the eye will not change. The image distance will not change on changing the object distance. The image distance of the eye will not change on changing the object distance, because the image is going to form on different positions at retina. Only the image is going to form at the different positions, but the distance between the retina and the image formation will not be affected in this case. So this is the answer for this problem, and now we are moving forward to the next question we have. Why do stars twinkle? This is again a very simple thing that we have discussed in our video lectures, that why do stars twinkle? Actually, whenever the starlight reaches the Earth's surface, what will happen? It has to suffer, or it has to pass from the medium of various refractive indexes. So sometimes the stars appear to you as a brighter, and sometimes the star appear to you as a fainter. So this dimming and fainter appearance of the stars is actually known as the twinkling of the stars. And twinklings of the star is basically due to when a starlight reaches the surface of the Earth, it will have to passes through the different refractive index medium, and whenever it is going to pass through the different mediums, it will suffer the total internal reflection. Okay, every time the atmospheric refraction is going to take place there, and the light is going to deviate from their normal path, and due to this, sometimes star seems brighter and sometimes it seems fainter, and this is the intensity of the stars that is changing continuously, is actually known as the twinkling of stars. Okay, so this is a very interesting phenomena we have observed in the nature. Now we are moving to our next problem. Explain why the planets do not twinkle. So this is again a very interesting question we have. Do you ever imagine that why do the planets do not twinkle? Actually, the planets do not twinkle because the planets are assumed to be a collection of large number of the point sources. Okay, so what we are assuming, that planets are collection of large number of point sources. If planets is a collection of large number of point sources, and if you are going to average, or you are going to sum up the intensity of light from all these point sources, then it came out to be 0, and if they came out to be 0, then they will nullify the twinkling effect, and that's why the planets do not twinkle. So if I am assuming that the planets are the large number of collection of the point sources, so on averaging the intensity from each point source, it comes out to be 0. It comes out to be 0, and if it comes out to be 0, then the twinkling effect will be nullified. Okay, this is the reason that the planets do not twinkle. Now, let's move forward to the next problem we have. Why does the sun appears reddish early in the morning? So, have you ever observed that why there is a red hues in the atmosphere at the time of sunrise or sunset? The main reason for appearing of sky or appearing of sun reddish in the morning is that the reason is that whenever the different intensities of the light, it means we have the different type of lights and the color of the sky is blue we have. So you know that when the blue light is scattered in the atmosphere, the scattering of the blue light will be the least. Why it is so? Because it is having a less wavelength. Okay, now if the blue color is not dominating much, then what is the color left? The color left is red, and we know that the red color has a maximum scattering because of its wavelength here. Okay, so the main thing that is responsible for the reddish color of the sun is that the blue color will not appear in much quantity, and its refraction is not going to take place in the atmosphere, and due to the greater wavelength of the red light, the scattering of the red light is seen in the sky. Okay, now this is the last question of our NCERT we have dealt today. So this is all about the NCERT questions from our chapter that is about the human eye and the colorful world. Now we will deal with NTSE questions in our next lecture. Thank you so much and have a great day.